Let us solve few problems on steam turbines. First, we'll solve few problems on single stage impulse steam turbine. Then we'll move on to multi-stage or two-stage impulse steam turbines. And later we will solve problem on reaction steam turbine. The first problem states that a single stage impulse turbine has a diameter of 1.5 meter and running at 3000 rpm. The nozzle angle is 22 degree. The speed ratio is 0.45. Ratio of relative velocity at the outlet to that at inlet is 0.9. The outlet angle of blade is 3 degree less than inlet angle. Steam flow rate is 6 kg per second. Draw the velocity diagram and find the following. First one, velocity of whirl. Second one, axial thrust. Third one, blade angles. Fourth one, power developed. In this problem, we have an impulse steam turbine which is a single stage. We need to remember that all steam and gas turbines are parallel flow turbines. All steam and gas turbines are axial flow turbines. So the velocity of the blade at the inlet and outlet of the blade will be same. That is, U1 will be equal to U2, and we can simply call it as U. Since U1 and U2 are same, we can draw a combined velocity triangle to solve these kind of problems. Okay, this has a diameter of 1.5 meter. They have not mentioned whether this is the mean diameter, diameter at the root, or the tip, but let us consider this as the mean diameter. So the mean diameter of the turbine is 1.5 meter and the turbine is running at 3000 rpm. The nozzle angle is 22 degree and the speed ratio is 0.45. Then the ratio of relative velocity at the outlet to that at the inlet is given as 0.9, which is nothing but the ratio of VR2 by VR1. So relative velocity at outlet is VR2 and relative velocity at inlet is VR1. So that means to say that it is blade friction coefficient denoted as CB. CB is 0.9. The outlet blade angle is 3 degree less than that at the inlet, which means to say that outlet blade angle is beta 2 and that is 3 degree less than the inlet blade angle, which is beta 1. That is, beta 2 will be equal to beta 1 minus 3. The steam flow rate is 6 kg per second. Now we need to draw a velocity diagram and then we need to find out the velocity of whirl, which is nothing but the velocity in the tangential direction, velocity of the fluid in the tangential direction, then axial thrust, that is the force in the axial direction, blade angles beta 1 and beta 2, and the power developed. First, let us list out the data. The diameter, I'll rate it as mean diameter is 1.5 meter. Then the speed is 3000 rpm. Then the nozzle angle is 22 degree, that is alpha 1 is 22 degree. Then the speed ratio, that is phi, is 0.45, which is the ratio of U divided by V1. Then the ratio of relative velocity is given, which is CB, that is 0.9, and the outlet blade angle is 3 degree less than that of the inlet, that is beta 2 will be equal to beta 1 minus 3. Beta 1 minus 3 degree. The steam flow rate is given, that is m dot mass flow rate of steam is 6 kg per second. Now I need to draw the velocity diagram and find out the first one, velocity of whirl. which is change in tangential component of the fluid. Then the second one is the axial thrust, which is denoted as FA, that is force in the axial direction. And the third one is we need to find out the blade angles, that is beta 1 and beta 2. And the last one is we need to find out the power developed, that is P. So these are the things which we have to find out now. To construct the velocity diagram, first we need to find out the value of u and v1. Whenever we are dealing with any triangle, there are 6 components that are present in a triangle. There are 3 sides and 3 angles. And if you want to construct any type of triangles, then you need to know at least any of the 3 values. So you may be knowing 2 degrees or 2 angles and a length of one side, then you will be able to construct a triangle. Or you may be knowing 3 degrees, then also you will be able to construct a triangle. Or you may be knowing 2 lengths or 2 sides length and 1 angle, then also you will be able to construct a velocity triangle. Out of 6 parameters, you need to know at least 3 parameters. For the inlet velocity triangle, the parameters are V1, U and VR1. Then we have alpha 1 and beta 1. So these are related to the velocity triangle. So out of this, alpha 1 is directly given, which is 22 degree. They have given the mean diameter and speed, so we need to find out u using those 2 data, and they have given the speed ratio. From that we will be able to find out v1. First let us calculate the tangential speed of the blade, that is u, which is given by pi d n divided by 60. So here the value of d is 1.5 multiplied by the value of n is 3000. We are dividing this by 60 just to convert RPM to RPS. So we will get the value of u as 235.6 meter per second. Once I know the value of u, I can easily calculate the value of v1. I know that phi is given by u by v1, and for this problem it is given as 0.45. So I need v1, which will be equal to u divided by 0.45, which is 235.6 divided by 0.45. If we calculate the value of v1, we get the value of v1 as 523.6 meter per second. Remember, the units are very important. So in each and every step, write the units. Now we know v1, we know alpha 1, and we know u. So I know 3 parameters in the velocity triangle. Now we should construct a velocity triangle, and then we need to calculate the required parameters. Now we need to choose a proper scale for our velocity triangle, and for that purpose here one rule of thumb is that in an impulse turbine, whether it is power producing or power absorbing impulse machine, V1, in the case of power producing impulse machines or turbines, V1 will be the longest side of the velocity triangle. So I'll choose a scale in such a way that since we will be using a smaller ruler in our examinations of 15 centimeters in length, so I'll choose the length of V1 in such a way that it comes around 10 centimeter. So it will be convenient for us to draw the velocity triangle on the sheet. Okay, so to do that, so here I'll take the scale as 1 centimeter will be equal to, I'll take it as 50 meter per second. So if I draw a 1 centimeter line in the velocity triangle, which it indicates that the velocity at that point is 50 meter per second. So according to that, if I choose that scale, then the length of V1, so I'll write it here. So length of V1 will be equal to around 10.47 centimeter, and length of U will be equal to around 4.7 centimeter. So while constructing the velocity triangle, I will be using this length. So now to draw the velocity triangle, I have inserted a ruler here. Now I need to construct the line. So I'll try to keep this at the center of the book. Now I need to draw a line for a length of 4.7 centimeter. This will be my U, and U will be in this direction. Now I need to construct V1. For that, first I will measure 22 degree. I'll keep the protractor here and I'll measure 22 degree. So I'll just put a mark here, approximately 22 degree. Then I'll take my scale and I'll rotate this over to that point. Then I'll draw a line. I'll not worry about the length of this line. I'm just drawing a line here. Then what I'll do is I'll take a compass and I'll measure the length. So the length of this should be equal to the length of V1, which you have calculated, which is 10.47. We won't be able to measure 47, so I'll just take it as 10.5. And I'll keep it on this point. Then I'll cut an arc. So where that arc cuts the 22 degree line, so from there I'll draw one more line. So I'll bring back my scale. I'll keep the end of the scale on this point, the other end of U, and I'll align this. Now I'll draw a line here. Now this is my V1 and this is my VR1. Now from this point I'll draw a vertical line. From here I'll just draw a vertical line, and from here I'll extend this horizontal line. I'll just extend this horizontal line. Now this is my VF1. This angle from here till here, this angle is beta 1, and this angle will be alpha 1. Now I need to measure the length of VR1. So I'll place the scale here, and we can see that the length of VR1 is around 6.4 centimeter. So VR1 is around 6.4 centimeter. Now with the help of CB, I need to calculate the length of VR2. VR2 will be equal to 0.9 times of 6.4, which will be equal to 5.8, approximately 5.8 centimeter. We get 5.76 centimeter, so that can be taken as 5.8 centimeter. Now I need to measure the angle made by VR1, that is, I need to measure V beta 1. So for that purpose, I place the protractor here. Now I can see that it is around 36 degree. So beta 1, I'll write it here. Beta 1 is around 36 degree. So I know the relation between beta 1 and beta 2. It is 36 minus 3, which is 33 degree. Now from the same point I'll measure 33 degree. So this is we'll get it somewhere here. So approximately here we have 33 degree line. I'll take my scale, I'll rotate it approximately here, and I'll place it here. Then I'll bring this over this. Now we need to draw this line from here. Again, I will not worry about the length of this line. I know the length of this line should be here it is 5.8. I will take the compass, I'll place it here. Now I will reduce the length to 5.8. Now it is 5.8. I need to place it on this point. Now I'll draw an arc. Now from this point I'll join the other end of U. So I'll keep the scale here. Now I'll join this too. Now this is our VR2. This is our V2. From this point we need to draw a vertical line, and from this we need to draw a horizontal line. It will be our VF2, and this length will be our V2. So now we have constructed the velocity triangle. So this will be from here till here, it will be our beta 2, and from here till here it will be alpha 2 dash, or this other side will be alpha 2. Now we need to measure few parameters here. So for that, first I'll draw projection lines. So from this point and from this point I'll draw another vertical line here. and from this point I'll draw a horizontal line. From this point I'll draw one more horizontal line. Now I need delta VU, which is this distance, and I need delta VF, which is the vertical distance between these two lines. Now let us measure these lengths. I'll make the scale horizontal. Now we can see that our delta VU is approximately 10 centimeter, and I'll change the scale to vertical. I'll reduce the length. Now if I measure this vertical distance, it's around 0.7. This is 0.7 centimeter. Only these are the parameters which we need for our calculation. I'll do the calculation in the next page. Now I have taken the value of delta VU as 10 centimeter and delta VF as 0.7 centimeter from the previous page where we constructed the velocity diagram and measured the values. Now the first thing which we have to calculate is the velocity of whirl. Velocity of whirl is nothing but the change in the tangential component of the absolute velocity from inlet to outlet, that is delta VU, which is equal to 10 centimeter, which we got it from the velocity diagram, multiplied by the scale, that is 50, so we will get it as 500 meter per second. Then we need to find out the axial thrust. Axial thrust is nothing but the force exerted in the axial direction, and the force is calculated as mass into acceleration. Here we are dealing with the flow of fluid, so I can write it as mass flow rate of the fluid into change in velocity in that direction. So here we are dealing with an axial flow turbine, so the change in the flow velocity will be the axial component of the absolute velocity, so the change in the flow velocity will give us the axial thrust. So to find out the change in flow velocity, so delta VF will be equal to 0.7, that is the length or distance which we measured, into 50, so we get it as 35 meter per second. And when we calculate the force, so force FA or the axial thrust will be equal to mass flow rate is 6 kg multiplied by 6 kg per second multiplied by 35, so we get it as 210 newtons. This is the force exerted in the axial direction. Then we had to find out the blade angles, which we have already measured. So beta 1 is around 36 degree and beta 2 is around 33 degree, that is 3 degree less than beta 1. Now we need to find out the power. Power is given by m dot into u into delta VU. So here the mass flow rate is 6 kg per second, and u, which we calculated in the previous case, that is 235.6 meter per second. 235.6 multiplied by delta VU is 500, so we get the power as 706.8 kilowatts, or so eta stage is given by eta blade into eta nozzle. Since the nozzle efficiency is not given in the problem, let us assume eta nozzle is equal to 100%. Now we need to find out the blade efficiency. So any efficiency is given by output by input. So here the output is the power developed by the turbine, that is m dot into u into delta vu, and the input energy for an impulse turbine will always be the kinetic energy, that is m dot into kinetic energy at the inlet, that is m dot into v1 square by 2. So mass per rate get cancelled here. So the efficiency of the blade, I'll just write it as eta b, will be equal to 2 times of u into delta vu divided by v1 square. When I substitute the values here, so this is 2 into 235.6 into delta vu is 500 divided by v1 is, so here we calculate the value of v1 as 523.6. 523.6 squared. It is around 85.9%. So we have to multiply this with 100 to get it in percent. So this is the blade efficiency. In this case, this is also the stage efficiency. Now let us solve the second problem. The problem states that one stage of an impulse turbine consists of a nozzle and one ring of moving blades. The nozzle is inclined at 22 degrees and the tangentials to the tangential speed of the blade, and the blade tip angles are equiangular and equal to 35 degrees. A. Find the blade speed diagram efficiency by neglecting losses if the velocity of steam at the exit of the nozzle is 660 meter per second. B. If the relative velocity of the steam is reduced by 15% in passing through the plate, then find the diagram efficiency and end thrust on the shaft when the blade ring develops 1745 kilowatts of power. Now in this problem we have two different cases. We have a single stage impulse steam turbine and the nozzle is inclined at 22 degree to the wheel to the tangential speed of the blade, and the blade tip angles are equiangular and equal to 35 degree, that is both beta 1 and beta 2 are 35 degree. In the first case we need to find out the blade speed and diagram efficiency by neglecting losses, that is by neglecting the losses if the velocity of the steam at the exit of the nozzle, that is the steam coming out of the nozzle with a velocity of 660 meter per second, that is v1 is 660 meter per second. In the second case, in the first case we have not considered any losses, but in the second case we need to consider those losses, that is the steam relative velocity of the steam reduces by 15%. So he has indirectly given the value of Cb. Now we need to find out the diagram efficiency if the power produced by the turbine is 1745 kilowatt. Now let us list out the data given in the problem. First, he says that it is an impulse turbine consisting of a nozzle and one ring of moving blade, and the nozzle is inclined at, that is alpha 1 is 22 degree. Alpha 1 is 22 degree, and the blade tip angles are given and they are equal, that is beta 1 is equal to beta 2 and that is given as 35 degree. Now we need to find the blade speed, that is we need to find u. For case A we need to find u, the blade speed, and then we need to find the diagram efficiency, is nothing but the stage efficiency, but here I have only the blade, no efficiency of nozzle is given, the efficiency of nozzle is not given, so I'll call that as eta b itself. And in this case v1 will be equal to 660 meter per second. In the second case we need to consider that the relative velocity of the steam is reduced by 15%. So the relative velocity is nothing but VR1 and VR2. So VR2 is reduced by 15% when compared to VR1, because for an impulse turbine VR1 and VR2 should be same. So here it is reduced by 15%. So I can say that VR2 by VR1, so this ratio will be equal to, in terms of plain numbers, it is 1 minus 0.15 times. So I can say that it has 0.85. This is the value of CB. So CB is 0.85. Now again we need to find out the diagram efficiency, that is eta B. I'll just write it as eta B dash, because we would have calculated eta B for the first case, when the power produced by the turbine is 1745 kilowatt. So this is the power produced by the turbine. For that case we need to find out the blade efficiency. Now since we have two different cases in the same problem, I'll be constructing the velocity triangle in the next page. So I'll be writing all the relevant data required again in the next page. So here we need alpha 1, which is 22 degree. Then I need beta 1 and beta 2, which are equal to 35 degree. Then I need V1, which is 660 meter per second. So these are the relevant data given in the problem. So I had noted down alpha 1, beta 1 and beta 2, then V1. Then we have CB here. CB is also required for the second case. First let us concentrate on the first case. So for the first case I will be drawing the velocity triangle with blue colored line. Now I will import the tools required for that. So I need a protractor, I need a ruler, and then I need a compass. So now on the center, almost at the center of the page, I'll place the scale and I will draw a line. Now in this problem we don't know the length of u. Actually we have to calculate the length of u. So for that purpose what I will do is I'll assume a scale. For an impulse turbine always V1 is the longest side. So I'll choose approximately scale, I'll take the scale as 1 centimeter equals 50 meter per second. So if I take 1 centimeter equals 50 meter per second, then the length of V1 will be around 13.2 centimeters. That is we can accommodate that in our 15 centimeter scale. So I'll take that scale. Now I don't know the length of u. So what I'll do is I'll just draw a horizontal line. I'll not bother with the length of u since I know beta 1. So I'll be able to construct the velocity triangle because I know two angles and one side length. So I know V1 and I know beta 1 and alpha 1. So we should be able to construct the velocity triangle. So now from this point I'll take the protractor, I'll place it exactly here, exactly over the line. Then I'll measure 22 degree. So here it's 22 degree. I have marked a point here. I'll bring my scale over here and then I'll rotate the scale over this point. Now I'll just draw a line from this point. Again I'll not bother with the length because I'll be using compass. I'll place the compass here. I know that the length of V1 will be equal to 13.2 centimeters on the diagram. So I'll increase this length to 13.6. Now I'll draw an arc. Now I have to extend the line, so I'll just place the scale over this and I'll extend this line. Now I have extended this line, so I'll take out all the instruments out of this. Now I know that this angle is alpha 1, which is 22 degree. Now I know beta 1, which is 35 degree, comes here, but I don't know where VR1 starts. So what I'll do is I'll take the scale and I'll draw a horizontal line here. From that point I'll draw a horizontal line. Now I'll take the protractor, I'll rotate it by 180 degree. Now I'll place it over this. Then I'll measure 35 degree and I'll mark it here. This is our 35 degree point. I'm using the concept of alternate angles. Now I'll join this. Now this is my V1, this is my VR1, and if I measure the angle here, that will be 35 degree. So that will be exactly 35 degree, because these two angles are alternate angles, because these two are parallel lines and we have drawn a straight line across the parallel lines, and if we measure these two angles they have to be same. So this is beta 1, which is 35 degree, and this will also be beta 1. So now I'll complete this. From this point I'll draw a vertical line and I'll extend this horizontal line over here. So this is my VF1. Now I need to complete this. So if I measure the distance from here till here, that will be our U. The length of U is approximately 5 point. This is U. It's 5.6 centimeters. Okay, we'll convert that into our units later. Now I'll bring this compass. I know beta 1 and beta 2 are same and there are no losses. So the length of VR1 will be, so the length of VR2 will be equal to VR1, and the angles are same. So that is 35 degree for both. So I'll measure 35 degree here. I have marked 25 degree here. Now I'll draw a line here. Again, I'll not worry about the length. I'll take the compass, I'll place it on this point. I'll measure this length, is 8.6 centimeter, and I'll cut an arc here. Now I'll take my scale. Now from this point I'll draw a vertical line, and from this point I'll draw a horizontal line. This is our VR2, and this angle is beta 2, which is also 35. This angle is alpha 2, and this is our V2, and this is VF2. So here in this problem we need to find out U as well as the blade efficiency. For blade efficiency, so I'll write the equation for blade or the diagram efficiency here, that is given by 2 into U into delta VU divided by V1 square. So I need to know V1, I need to know U, and I need delta VU. So from the velocity triangle, now I'll measure delta VU. For that, I need to measure the horizontal distance between VF1 and VF2. So here I'll draw a vertical line, and here also I'll draw a vertical line. Around 14.1 centimeter. So delta VU is around 14.1 centimeter. That's all we need for our problem. I know the length of U as 5.6 centimeter, so I can calculate U here. So from graph or from velocity triangle, U will be equal to 5.6 into 50, which is equal to 280 meter per second. Now the diagram efficiency, or in this case the blade efficiency, will be equal to 2 into U, which is 280, multiplied by, I need delta U, I'll just calculate here, delta VU will be equal to 14.1 into 50. So 14.1 into 50 will be around 705 meter per second. So 705 divided by V1 square. V1 is 660 meter per second. So it's 0.906. The diagram efficiency is 90.6%. Now we need to solve the same problem for the second case. This is for case A. For case A. Now we need to solve the same problem for case B. So the only difference between case A and case B is that in case A we neglected the losses, but in case B we have to consider the losses. There is no change in the blade angles or the inlet conditions. So now the only change which has to happen is in VR2. Now for case 2 I'll be using yellow color. So here CB is given as 0.85, which is equal to VR2 divided by VR1, which says that VR2 will be equal to 0.85 times of VR1. Since we know the length of VR1 here, we can measure the length of VR1 here. So for that, I'll just take the scale, keep it here, and I'll adjust the angle so that we will be able to measure the length of VR1. So the length of VR1 is approximately equal to 8.6 centimeter. Now the length of VR2 will be equal to 0.85 times of 8.6 centimeter, which is 7.31 centimeter, which can be taken as 7.3 centimeters. Now I'll take this compass, I'll change the angle, I'll place it here on this point, and I'll reduce the length to 7.3. Now on VR2 I'll draw one more arc. So where this arc cuts VR2 line, from there I'll just join this with U. This is our new V2. So I'll call this as V2 dash, and I'll draw a vertical line from here. From this point I'll draw a vertical line, and then I'll draw a horizontal line here. So this is our VF2 dash, and this will be our VU2 dash. So now for this I need to measure delta VU. So from here I'll draw a vertical line. So this was delta VU for the first case. Now this will be our delta VU for the second case. So I have to measure this. I'll take this ruler again. Here we can see that it is 13 centimeter. Now for the second case, I'll write it as delta VU dash as 13 centimeter. So I have to use this data to calculate the required parameter. So here for the second case I need to find out the blade efficiency. Again I'll call this as delta B dash, which will be equal to 2 into U will not change, delta VU dash divided by V1 square. Okay, here let us calculate delta VU dash, which is equal to 13 into 50. So this is 650 meter per second. So now let us calculate the diagram efficiency for the second case. That is 2 into U is 280 into 650. If you observe case 1, case A and case B, so in case A the tangential change in tangential velocity component was 705, but here it is reduced to 650 t square. So now this ratio, that is eta B dash, is around 0.8356, or eta B dash is 83.56%. Now the efficiency has also reduced. So this is the actual case where the efficiency matters, because here we are considering the losses. In the first case, that is case A, we had just considered only the theoretical velocity diagram without any losses, or the ideal case, but here we are considering the actual case where there is a reduction of 15% in the relative velocity, and that results in a reduction of around 7% of efficiency. Now let us solve problem number 3. The problem states that steam flows through a nozzle with a velocity of 450 meter per second at a direction which is inclined at an angle of 16 degree to the wheel tangent. Steam comes out of the moving blades with a velocity of 100 meter per second in the direction of 110 degree with the direction of blade motion. The blades are equiangular and the steam flow rate is 10 kg per second. Find the power developed, the power loss due to friction, axial thrust, blade efficiency, and blade coefficient. So here again we have an impulse turbine where the velocity of steam, that is V1 is given as 450 meter per second, and this is coming at a direction of 16 degree to the wheel tangent. So this is all alpha 1 is 16 degree. Now steam comes out of the moving blades with a velocity of 100 meter per second. So here he is talking about the fluid coming out of the moving blade. So this is the absolute velocity of the fluid, not the relative velocity. So V2 is given as 100 meter per second in the direction of 110 degree with the direction of blade motion. So the direction of blade motion is nothing but u. So he has given the angle with respect to u, which I'll call it as alpha 2 dash as 110 degree. I'll show the where we get alpha 2 dash and the alpha 2 in the velocity diagram. So I can write alpha 2 will be equal to 180 minus alpha 2 dash. So this will be around 70 degree. So alpha 2 is given as 70 degree. The blades are equiangular, which means to say that beta 1 will be equal to beta 2, and the mass flow rate of steam is 10 kg per second. So with this given data, we need to calculate first one, the power developed, second one, the power loss due to friction. I'll write it as PFL, frictional loss. Then third one, we need to find out the axial thrust, which is FA. Then fourth one, we need to find out the blade efficiency, that is eta B. And fifth one, we need to calculate the blade coefficient, which is CB, or the blade friction coefficient. Again, we need to construct the velocity triangle. Here I don't know the length of u. Here he has not given any data related to u. He has given alpha 1 v1, alpha 2 v2, and he says that beta 1 and beta 2 are same. So with these available data, we should construct the velocity triangle, and then we need to find out u, and then we need to find out the required parameters. So first, let us try to construct this. Again, I don't know the length of u. So at the center of the page, I'll draw a horizontal line. I don't know the length. I'll just draw a horizontal line. Now I know the length of u, sorry, v1. Now I know the length of v1, and okay, before drawing the velocity triangle, let us list out the data in this page. So alpha 1 is given as 16 degree, v1 is 450 meter per second, alpha 2 is 70 degree, which we calculated, and v2 is given as 100 meter per second. Then beta 1 is equal to beta 2. So these are the data given in the problem. Again, we will choose a suitable scale. So here I prefer a scale of since our here I'll take the scale as 1 centimeter equals 50 meter per second. So by this I know the length of v1 will be equal to 9 centimeters, and the length of v2 will be equal to 2 centimeters. I know the angles and I know the length. So first what I'll do is I'll just mark the angles for v1 and v2. So v1 I have to measure from this side, and that is 16 degree. So here we have 10, this is 15. So here we have 16 degree, and for v2 I have to measure from this side, and that is 70 degree. So from this side 17, or from this side 110 is here. I'll place a mark here. I'll move it. Now I need to draw lines for V1 and V2. So I'll place at this end and I'll tilt this till I reach this point. Now I'll draw a line. I'll not bother with the length. Now I know it should be 9 centimeter, so I'll place it here. I'll change the length to 9 centimeter. Then I'll cut an arc. Once I have done that, now what I'll do is I'll complete the inlet velocity triangle. So from here I'll draw a vertical line. Now this is VF1 and this is our V1. Now I don't know where I'll get VR1, but since I know V2 and alpha 2, I'll construct those two also. So I'll place the ruler over here. I'll mark 2 centimeter with the help of scale itself. Now from this point I'll draw a vertical line. Then I'll complete this triangle. Now this is VF2 and this is V2. Now with the help of this we'll be able to find out delta VU and delta VF. If those two are the only required parameters, then we don't have to worry about further construction. But here we need to find out the power loss due to friction. So for that we use the term friction in VR1 and VR2. So I need those two values. So what I'll do is is 1.9 centimeter. Here I'll just explain the concept. Here we have two triangles. Now I know this angle, so if I have to complete this, we'll have a triangle like this. Now I know these two angles are same, beta 1 and beta 2 here. Those two angles are same, and I know this height is same. So this height is common for this triangle as well as this triangle. So what I'll do is, if I draw the same height below the line and if I join this, then these two triangles will be a similar triangle because the heights are same and these two angles will be same. Since the height is same and one of the angle is 90 degree, so the other two angles, so this length, this side is common for both the triangles, so the angles will be same. So this will also be equal to beta 2, which is also equal to beta 1. So if I draw a line, a horizontal line and then a straight line, and then if the newly drawn line is straight line, then these two angles will be same. So this will beta 1 in our case, this is beta 2, which is also equal to beta 1. That is the data given in the problem. So this forms a straight line. So I am using this concept here to construct or to find where we will this line, that is the length VR1 and VR2 line, will intersect the horizontal line over here. So now the height of VF2 is around 1.9 centimeter. So I'll take that for a length of 1.9 centimeters. So now I have drawn a line here. Now what I'll do is I'll just simply keep the scale here and I'll extend this and I'll bring it to this point. I place it over the apex of the first or the inlet velocity triangle. Now I'll join these two wherever this line intersect the horizontal line. So that will be the length of, from here till here will be the length of U. This is our U and this is our VR1. Now what I'll do is from this point I'll join the apex of the outlet velocity triangle. So for that I have to rotate the scale. I'll keep it here for this point and I'll adjust the scale. Now I'll join these two. From this point till here I'll draw a line. So now this is our VR2. Now if I place the compass, now if I place the protractor over here, you can see that these two angles are 25 degree. They are matching perfectly with each other. So now this completes the construction of the inlet as well as the outlet velocity triangle. Now we need to measure the lengths. So I'll write the lengths here. I need delta VU, I need delta VF, I need VR1 and also I need VR2 length. First let us find out delta V1 and delta V2. So for that, from here I'll draw a vertical line and also from here I'll draw a vertical line. So if we measure, it is around 9.3. So delta VU is around 9.3 centimeter. So delta VU is 9.3 centimeter. That is from here till here. This is 9.3 centimeter. Now I need delta VF. For that purpose, I'll draw two horizontal lines, one from the each from the apex of the inlet and outlet velocity triangle. Now I need to measure the vertical distance between these two, and that will be our delta VF. Again, I'll take the scale, I'll rotate it vertical, then I'll place it over here. It's around 0.6 centimeters. So delta VF is 0.6 centimeter. Now we are done with the construction. So delta VF is 0.6 centimeter. Now I need to measure VR1. Place the scale here and I'll rotate it parallel to VR1, and that is, the length is 5.8 centimeters. So it is 5.8 centimeter. Now I'll rotate it over to VR2. Now the length is around 4.5. centimeter. So these are the required data. Now these are the required data. Now let us calculate the parameters. So I'll go back to the problem. So we'll just convert this into meter per second here itself. So this will be 9.3 into 50, which is 465 meter per second. And this is 0.6 into 50, which is 30 centimeter. Then this is 5.8 into 50, which is 290 centimeter per second. Then this is 4.5 into 50, which is 225 meter per second. So I'll be transferring these values to page 1. Delta VU is 456 meter per second. Sorry, 465. 465 meter per second. Delta VF is 30 meter per second. Delta VF is 30 meter per second. VR1 is 290 and VR2 is 225 meter per second. VR1 is 290 meter per second. VR2 is 225 meter per second. Now let us calculate the first parameter, that is the power. Power is given by m dot into u into delta VU. Oh, we forgot to measure the length of u. That is very important in this problem, since we don't know the length of u. We have constructed the velocity triangle like this. So I'll take the ruler again. I'll place it over here, and from the diagram we can see that it is around 3.3. The length of u is around 3.3 centimeter. So 3.3 into 50 will give us 165 meter per second. M dot is 10 kg multiplied by u is 165 meter per second. 165 into delta VU is 465. So the power developed by the turbine is 767.25 kilowatt. So this is the power developed. Now we need to find out the power loss due to friction, PFL. So here we are considering the friction Here we encounter the friction, and that results in the reduction in the relative velocity from inlet to outlet. So to find out the power loss due to friction, we have to use that. The power loss due to friction is given by VR1 square minus VR2 square divided by 2. This is the energy loss due to friction. For that, if I multiply the mass flow rate, then I'll get the power loss due to friction. So let us substitute the values here. So m dot is 10 multiplied by 290 square minus 225 square divided by 2. So the power loss due to friction, that is the frictional power loss, is equal to 167.37 kilowatt. So this is the amount of friction energy we are lost. This is the amount of energy we are losing due to friction. Now let us calculate the axial thrust. So the axial thrust is given by m dot into the change in velocity in the axial direction, that is delta Vf. So this is 10 into 30, which is 300 newtons. So this is the axial thrust acting on the shaft. Then we need to find out the blade efficiency, eta B. So eta B is given by 2 into U into delta Vu divided by V1 square. Here let us substitute the values, that is 2 into U is 165 multiplied by delta Vu is 465 divided by V1 square. V1 is 660 square divided by V1. V1 is 450 square. This is around 0.757 or 75.7%. That is the blade efficiency. Now we need to find out the blade coefficient, that is CB, which is given by VR2 divided by VR1. So VR2 is 225 divided by VR1 is 290. So CB will be equal to 0.775. This is the blade coefficient or blade friction coefficient.